Okay, so we're going to do part 2 of the Tension Force Lab. It's really an exploration using EdPuzz for instructions to give you the opportunity to discuss things with your group. So I just want to remind you where we're going is that we are starting with this idea of two people pull on the end of a single spring, and we know that they have to pull with the same force because it's the same spring. And then we have multiple bridging examples, and finally the target is to be able to predict which situation with Spider-Man would cause the most discomfort, horse and tree, horse and horse, or are they equal? And we're going to use microscopic models that we've already kind of seen to some extent to help us know what the answer is. So that's where we're heading. Before we get there, I have looked at the homework, and consistently people got this question wrong. And so I think only 1 or 2 groups got it correct. And so I want you to actually do this experimentally. So remember the homework, we've got 3 identical springs are connected to a wall on the right and a block on the left. A person pulls on the rope so the scale reading is 450. So over here we have 450 newtons. And we want to know how much force is exerted on the wall by one of the springs and how much force does the rope exert on the wooden block. So we want to know what is the force here, and then we want to know basically what's the force here, here, or here. So I want you to set this up using 4 identical springs. So instead of having a spring scale here, you're actually going to put another spring. And you're going to use the length of the springs to determine the size of the force, because we know that the length of the spring is proportional to the size of the force. And so measure this and see what you get. Okay, so for this example, we know that we're not moving, and so what that means is that the forces are balanced. And so I want you to create a free body diagram that shows that the forces are balanced. So I've got 1 spring on this side, 3 springs on this side, and you can look at the forces on the block. So do a free body diagram for the block. And what I want to know, and you should put in the values that you have, and you can make up a value for one of them, and then based upon the relative length, come up with the values for the other 3. So what we want to know is, does your free body diagram make sense with what you found for the length of the force on each of the springs? So for example, if one spring is twice as long as the other, then we know it's twice the force. So I want you to just arbitrarily assign a value to like this spring, or you could also do it to one of these springs, and then based on lengths, determine values for the other 3 springs, and then use your free body diagram of what's on the block. So block, you'll have forces going. Determine if it makes sense or if the forces are actually balanced. So let me know if you're confused by that. Okay, so our bridging example. Okay, so we've got a spring attached to a tree with a spring in the middle and then a spring on the right. And the man on the right is pulling the spring with a force of 100 newtons. And we want to know how much force does the tree exert on the left spring. So we've got 3 options. Okay, so when we look at this example, how does this compare to our target problem, which is trying to determine, does Spider-Man feel equal discomfort with these, more discomfort with the horses, or more discomfort with the tree and the horse? So we want to know, how does this compare to our target problem? Okay, next thing. All right, so the system adjusts to changing forces, and hopefully this is something you've actually experimented with as you've been playing with springs, but in case you haven't, we're going to do it explicitly. So we're going to do the same example as before. So spring attached to something tree-like, find something in the lab. And instead of pulling with 100 newtons, the person's going to pull with 200 newtons. And does the force here change? And if it does, how? How does the system know to change the value of this force based upon the value of this force? So what happens to the force throughout the entire system? Okay. All right, so I won't go into a whole lot of molecular detail unless you want me to, because it's actually pretty straightforward. But the idea is that the tension has to equalize throughout the entire system. So we can start over here. If the person is pulling to the right with 200 newtons, then we know at the end of this spring, there's a pull to the left of 200, which means that because these are attached, if this is left 200, then we know that this spring, this end of the spring, is right 200. Well, if this end of the spring is right 200, we know this end of the spring is left 200, because again, the ends of the spring, I've got equal tension. All right, these are attached, so if the right spring, or if this end is pulling this way with 200, we know this end is pulling this way with 200, because again, this string between the springs has the same tension. So this end of the spring has 200, so that means this end of the spring has 200. This end of the string has 200, which means this end of the string has 200. It's the same everywhere. So if this end of the string has 200, that means the tree has to have 200. Okay, and the tree you can think of as just another spring, or it's stretchy material. So if left is 200, right is 200, that means left has 200. So the idea is that if I have springs, if one stretches, they all stretch equal amounts. So think of a rubber band. You would never have a rubber band that is stretched on one part and not stretched on the other part. So if you want to try it out with a rubber band, and as a matter of fact, it stretches equal amounts. If you want to try it out with a rubber band, there should be one, and you can look at the marks on the rubber band. But when it stretches equal amount all over. And so that's how the system knows that it has to equalize throughout, is that the moment I make a change in one part of a system, it makes the part everywhere. It makes the change everywhere. Okay, so here is our final bridging example. All right, so I've got my two horses. Horse on the right is pulling, horse on the left is pulling. They're pulling with equal amounts, okay? All right, so I back them up. So the string is attached to the tree. They're pulling with equal amounts. And all of a sudden, I clamp this down, okay? Again, I don't change anything. This horse is still pulling the same as it was before. It's just now I'm clamping it down, and this horse goes away. Okay. Does the tension on this side change at all? Just by clamping it down here. So before the clamp versus after the clamp. Does anything change? Okay, so we want to vote again, all right? I want to discuss again. Which situation causes the most discomfort for Spider-Man? Two horses, a horse and a tree? The situations cause equal discomfort. So why does this happen? So we've already talked about this. We talked about this in the first tension video, and that is we got this springy model of the atom. And so all solid matter, we can think of it as made of a bunch of little springs where we have atoms between the springs, and these springs are actually the bonds, and the bonds are stretchy because the electron clouds, they can expand with tension or they can compress with normal. Okay, so springy model of the atom is how this happens, and when you pull on one part, it's like the electrons kind of equalize the springiness all over. All right, so here's our final experiment. I want you to predict first, okay? On the end scales, we're gonna read, pull it until there's 2.5 newtons, 2.5 newtons. What is gonna be the reading on the middle scale? So I want you to predict it first, and then do it. Okay, now we're going to make it slightly different, okay? You're going to attach this to something, like a ring stand. Okay, so you're going to attach it, and you're going to pull on this side so that the spring scale reads 2.5 newtons. What does this one read? What does this one read? Predict, then do it. All right, last discussion. Hopefully you got it. Which situation causes the most discomfort for Spider-Man? Okay, so we're going to define tension. Tension is the magnitude or size of the force on one end of any solid object that is being pulled. It really can be any solid object, but usually we think of things that are string-like, such as a rope, chain, bungee cord, wire, but it could be a piece of metal. Like if you're hanging from a piece of metal off of a jungle gym or something, tension is the size of the force on one end. It's also the reading you would get when placing a spring scale anywhere in the rope or string-like object. So you could cut that string-like object anywhere and put in a spring scale, and it's that spring scale reading. Tension results as atoms or molecules of the string-like object are pulled apart. Not apart completely, but they are pulled away from each other because the bonds between atoms are springy. They're made of electron clouds. And then tension is a force, so the unit is newtons, capital N. Okay. All right, one last thing. So pulleys and tension. So sometimes you have a rope going over a pulley, and I want you to know that going over a pulley does not change the tension in the rope. So a pulley is a frictionless, massless device that changes the direction of a rope without changing the tension in the rope. So what I want you to do is attach a spring scale to something like the ring stand, and then on the other end of like the fishing line, you're gonna put it over a pulley. I've got clamps that you can put on the end of the lab bench. Put them over a pulley and have a spring scale on the other side, and you want to pull and instantaneously read here and here. You have to read at the same time or you will probably get different results. So you want to read in multiple angles. And to prove to yourself that it doesn't matter like how I bend this rope over a pulley, as long as this is frictionless, whatever I'm reading on this end is what I'm reading on this end. The tension is the same everywhere in the rope. So hopefully you are comfortable with that because this is your last chance to kind of learn tension is the same everywhere in the rope. And on to group worksheet 2.